Hello everyone, let's review the autumn semester of the Fluid Dynamics module. First, let's discuss the Continuum Hypothesis. It says we can assume that we can unambiguously describe properties of a fluid flow at a point in space, such as density, velocity, and acceleration. Now, let's move on to discussing Eulerian Coordinates. In Eulerian Coordinates, x with t, the state of a fluid, e.g. velocity or pressure, is described in terms of their values at a fixed location in space, x, and at a fixed time, t. The Euler equation of fluid motion is usually written in these coordinates. Next, let's compare this to Lagrangian coordinates. This is where we study the motion of individual fluid particles, and reference is made to the state of the system at some appropriate point in history of the fluid motion, for example at time t equals 0. Fluid particles at later times are described in terms of their original positions in the reference state. So, for example, a fluid particle at a general time t is located at the point x of alpha t, where t is the present time and alpha is the position vector of the particle in the reference state at time t equals 0. So, the velocity of this fluid particle is u is equal to the partial derivative of x with respect to t sub alpha, where the subscript alpha reminds us that we're referring to individual fluid particles which started at alpha at t equals 0. We refer to alpha t as Lagrangian coordinates for the flow. Next, let's define some terms relating to velocity. In Cartesian coordinates, we write velocity of the fluid particle at a point with coordinates x, y, z as u of x, y, z, t is equal to u of x, y, z, t I plus v of x, y, z, t j plus w of x, y, z, t k. If the fluid velocity depends on time t, we say the flow is unsteady. If it does not depend on t, the flow is steady. The flow speed is given by the modulus of u is equal to u squared plus v squared plus w squared square rooted. A stagnation point is a point where the velocity vanishes, i.e. u is equal to the zero vector. A flow is two-dimensional if everywhere and for all time, the partial derivative of u with respect to z is equal to the partial derivative of v with respect to z, which is equal to 0, and w is equal to 0. Next, let's move on to discussing plane polar coordinates for 2D flows. For a general point P with Cartesian coordinates x, y, the plane polar coordinates are r theta with x equals r cos theta and y equals r sin theta. So r hat is equal to cos theta I plus sin theta j, and theta hat is equal to minus sin theta I plus cos theta j. Now, let's move on to defining streamlines. A streamline is a curve C drawn in the fluid at one instant of time such that the fluid velocity vector is tangent to C at every point on C. For an unsteady flow, the pattern of streamlines changes with t. The starting point in streamline problems is dx over u is equal to dy over v, which is equal to dz over w. Now, let's contrast these to particle paths. Consider a fluid particle at a point P with position vector x0 is equal to x0, y0, z0 at some fixed time t equals 0. As t increases, the fluid particle moves through space. Its path is known as the path line or particle path. A particle path is computed by solving the initial value problem dx over dt is equal to u of xt and x is equal to x0 at t equals 0. For each chosen x0 there is a particle path. Writing in components, we have dx over dt is equal to u, dy over dt is equal to v, dz over dt is equal to w, with x of 0 equal to x0, y of 0 equal to y0, and z of 0 equal to z0. Now, let's move on to giving some useful vector identities. First, we have that the curl of grad phi is equal to the 0 vector for any phi. Second, we have that the divergence of the curl of u is equal to 0. Third, we have that u cross curl of u is equal to grad half u squared minus u dot grad of u. Now, let's move on to discussing the Divergence Theorem. Let W be a vector field, V be a volume in 3D space with surface S and outward normal n. Then the double integral W dot n ds is equal to the triple integral over V of the divergence of W dV, where ds is an element of surface area of S. Note there is also the scalar equivalent of the divergence theorem that the double integral over S of Pn ds is equal to the triple integral over V of grad P dV. Next, let's discuss Stoke's theorem. Let C be a simple closed curve in space with dr tangent to C, and suppose C is spanned by a surface S with unit normal n. Then the double integral over S of the curl of W dot n ds is equal to the integral over C of W dot dr. Note that if you look towards S so that the unit normal n points towards you, then the direction of traversal is anti-clockwise around C. Next, let's discuss the convective derivative. It represents how a quantity changes as it moves with a flow. It is sometimes called the substantial derivative or the material derivative. It is written as capital D over capital dt, and in general it takes the form capital D over capital dt is equal to the partial derivative with respect to t plus u dot grad, which is equal to the partial derivative with respect to t plus u times the partial derivative with respect to x plus v times the partial derivative with respect to y plus w times the partial derivative with respect to z. Now, let's move on to discussing vorticity. Vorticity, omega, is a measure of the local rotation of fluid particles in a flow. Vorticity is related to the velocity field by vorticity is equal to the curl of u. For a 2D flow, we have that u is equal to u of xyi plus v of xyj, so the vorticity is omega, which is equal to the curl of u, which is equal to the partial derivative of v with respect to x minus the partial derivative of u with respect to y, k. So, for a 2D flow, the vorticity is normal to the plane of the flow. Note that we say that a flow is irrotational if omega is equal to the zero vector everywhere in the flow. Next, let's discuss incompressible flows. A flow with velocity field u is said to be incompressible if the divergence of u is equal to 0. Essentially, this means that fluid volume is preserved. Note that if a flow is incompressible, it is also true that the convective derivative capital D rho over capital dt is equal to 0. Also note that if the divergence of u does not equal 0, then the flow is compressible. Now, let's move on to discussing the velocity potential. For an irrotational flow, the curl of u equals 0, and we define a velocity potential phi so that u is equal to grad phi. If a flow is both incompressible and irrotational, then we can define a velocity potential phi so that u is equal to grad phi to satisfy that the curl of u is equal to the 0 vector. Then, the Laplacian of phi is equal to 0. Hence, let's give a physical interpretation of velocity potentials. The velocity potential phi is defined so that u is equal to the grad of phi. We say that lines or surfaces of constant phi are called equipotentials. Consider the surface phi of xyz is equal to c for some constant c. Then, the gradient grad phi is normal to this surface, and the direction of maximal change of phi is in the direction of grad phi. Consequently, the velocity is always normal to equipotential line. Now, let's move on to discussing pressure in a fluid. Consider a small element of area delta S lying on the boundary of a region occupied by a fluid. Let n be the unit normal to this element pointing into the fluid. The fluid exerts a force delta F on the area element perpendicular to the element. So, delta F is equal to delta Fn, and delta F is equal to the modulus of delta F. The pressure P on the area element is defined by P is equal to the limit as delta S approaches 0 of delta F over delta S. So, for a general area S, the total force on S due to the fluid is F, which is equal to minus the double integral over S of Pn ds, where n is the unit normal into the fluid. Note that if the surface is curved, n is in different directions at different points on S. Now, let's start discussing equations of state. The equation of state relates the pressure P and the density ρ. For a liquid, the density is constant, and that is independent of pressure. Next, let's state the ideal gas law. For an ideal gas, the pressure P, the density ρ, and the temperature T are related by the ideal gas law P over ρT is equal to a constant. Then, let's discuss isothermal gases. If the temperature is constant, we say that the gas is isothermal. Then, pressure is proportional to density, which is Boyle's law. We can write this as P times ρ to the minus 1 is equal to P0 times ρ0 to the -1, where P0 and ρ0 are the pressure and density in the reference state. Then let's discuss adiabatic gases. If fluctuations in pressure occur quickly, such as in sound waves, then the pressure and density are related by the adiabatic law P times rho to the minus gamma is equal to a constant, where gamma, the polytropic index, is a constant. Now, let's move on to consider hydrostatics. Consider a large volume of stationary fluid and a smaller region R of fluid within this volume. The surface of this region is taken to be S, with N, the unit normal, pointing out of R into the surrounding fluid. Since the fluid is stationary, the weight of the fluid in the volume must be balanced by a force on R due to the pressure P of the surrounding fluid. We have that the total force on R is F, which is equal to minus the double integral over S of Pn ds, and applying the scalar divergence theorem, F equals minus the double integral of S Pn ds, which is equal to minus the triple integral over R of grad P dV. If the density of the fluid is P in a gravity field G, the total weight W of the fluid in region R is W, which is equal to the triple integral over R of rho g dV. Since the fluid is stationary, the total force on the fluid inside R is 0. So F plus W, which is equal to the triple integral over R of Pg dV minus the triple integral over R of grad P dV is equal to 0. Hence, the triple integral over R of Pg minus grad P dV is equal to 0. Since this result must hold for all regions in R, we have that grad P is equal to rho g. Since g is equal to minus gk, this vector equation is equivalent to three scalar equations. The partial derivative of P with respect to x is equal to 0, the partial derivative of P with respect to y is equal to 0, and the partial derivative of P with respect to z is equal to minus rho g. So P is independent of x and y, and thus P can only be a function of z. Thus, if ρ is known as a function of P from the equation of state, then P can be found as a function of z. Now, let's move on to discussing buoyancy. For a body in a static fluid, the buoyancy is the force due to the pressure of the surrounding fluid. Consider a body occupying a region V completely submerged in a fluid of density ρ. The buoyancy force is given by B is equal to minus the double integral over S of Pn ds, where S is the surface of the body, N is the unit normal out of the body and into the surrounding fluid, and P is the pressure at the surface of the body. The pressure on S is the same irrespective of what is inside S, so it's convenient to think of S as containing the same fluid as the surrounding fluid. In this way, we can apply the divergence theorem to get that B is equal to the minus the double integral over S of Pn ds, which is equal to minus the triple integral over V of grad P dV, which is equal to K times G times the triple integral over V of rho dV. Hence, B is equal to rho V gk, which is equal to mw gk, where mw equals rho V is the mass of the fluid displaced by the body. This is Archimedes' principle, i.e. the buoyancy force on a body is equal in magnitude to the weight of the fluid that it displaces by the body, and the direction of the buoyancy force is upwards. The same result holds for partially submerged bodies. Now, let's move on to discussing conservation of mass. Consider a closed volume V which is fixed in space inside a moving fluid. As the fluid moves past, the rate of change of the mass of the fluid within V must equal the net amount of fluid coming into or out of it, assuming there are no sources of fluid within V. So, the equation of conservation of mass, also known as the continuity equation, is that the material derivative D rho over dt plus rho times the divergence of u is equal to 0. Now, let's discuss Euler's equation of motion. It states that the partial derivative of v with respect to t plus u dot grad u is equal to 1 over rho grad p plus g. It is accompanied by the equation of conservation of mass, which for an incompressible fluid is that the divergence of u is equal to 0. Next, let's discuss boundary conditions. At a fixed, impermeable surface, the normal component of fluid velocity at any point on the surface must be 0. Mathematically, this means that u dot n equals 0 at the surface, where n is the unit normal to the surface. Hence, at a fixed impermeable surface, u must be directed tangent to the surface. Next, let's discuss Bernoulli's equation for irrotational flows. For an irrotational flow, Bernoulli's equation is that p over rho plus the partial derivative of phi with respect to t plus a half u squared plus gz is equal to f of t, where the function f is often a constant. Next, let's consider Bernoulli's equation for a steady flow. It says that p over rho plus a half u squared plus gz is equal to b, where b takes the same value along a given streamline, but for different streamlines, the value of b will be different. Now, let's consider an application of Bernoulli's equation, a flow in a tube. We allow for tubes whose cross-sectional area varies along the tube. So, consider a section of tube with starting cross-sectional area a1, starting velocity u1, final cross-sectional area a2, and final velocity u2. The total volume flux in through a1 must equal the total volume flux out through a2. Hence, u1 a1 must equal u2 a2. We can apply the steady form of Bernoulli's equation on the streamline along the tube centerline. So, on the streamline, we have p over rho plus a half u squared plus gz is equal to b for Bernoulli constant b. Now, let's move on to discussing calculating a velocity potential. If the flow is irrotational and incompressible, the velocity potential satisfies the Laplace equation that the Laplacian of phi is equal to 0. For a solid fixed boundary S, we have that the boundary condition is n.u is equal to 0. So, n.grad phi is equal to 0 on S. This is written as the partial derivative of phi with respect to n equals 0 on S, using the notation that n.grad phi is equal to the partial derivative of phi with respect to n to mean the derivative in the n direction. For example, if the surface is a sphere, radius a, centered at the origin, then the normal to the surface is in the radial direction, so the boundary condition becomes the partial derivative of phi with respect to r is equal to 0 on r is equal to a. Next, let's discuss the stream function. For any 2D flow that is incompressible, we can write the velocity in the form u is equal to the partial derivative of psi with respect to y, and v is equal to the partial derivative of psi with respect to x multiplied by -1, where psi of xyt is the stream function. Note that this definition of psi is equivalent to saying that u is equal to the curl of psi of xy k. Note that psi of xy is constant on a streamline. Thus, by finding the contours of psi, we can find the streamlines of a flow. Note that the magnitude of u is inversely proportional to the distance between streamlines. And notice that in plane polar coordinates, psi of r theta is given by u is equal to ur r hat plus u theta theta hat, where ur is equal to 1 over r times the partial derivative of psi with respect to theta, and u theta is equal to minus the partial derivative of psi with respect to r. Next, let's discuss the relationship between the stream function and vorticity. For a 2D flow, the vorticity is omega is equal to omega k, where omega is equal to vx minus uy. Substituting the expressions for u and v in terms of psi, we have that omega is equal to minus the second partial derivative of psi with respect to x minus the second partial derivative of psi with respect to y. Hence, the stream function psi satisfies the Laplacian of psi is equal to minus omega. Then, let's discuss how stream functions and boundary conditions relate. At a solid, impermeable boundary, the boundary condition is one of no normal flow at the boundary. This implies that the boundary is a streamline. Hence, psi is constant on the boundary. Now, let's move on to discussing the velocity potential of a line vortex. Consider a flow with velocity potential psi is equal to gamma over 2 pi theta, where gamma is a constant. Then u is equal to grad phi, which is equal to the partial derivative of phi with respect to r times r hat, plus 1 over r times the partial derivative of phi with respect to theta times theta hat, which is equal to gamma over 2 pi r theta hat. Hence, the velocity is entirely in the theta hat direction, and the modulus of u tends to infinity as r tends to 0. The components of velocity are ur equals 0 and u theta is equal to gamma over 2 pi r. Calculating the stream function, we have that ur is equal to 1 over r times the partial derivative of psi with respect to theta, and u theta is equal to minus the partial derivative of psi with respect to r. Hence, 1 over r times the partial derivative of psi with respect to theta equals 0, and minus the partial derivative of psi with respect to r is equal to gamma over 2 pi r. Integrating both equations leads us to psi is equal to minus gamma over 2 pi log r. The streamlines are given by psi as constant, which implies that r is constant. So, the streamlines are concentric circles centered on the origin. We call this flow a line vortex. It is a 2D flow whose fluid move in a circle about the origin. Next, let's define a vortex. A vortex is a concentrated region of vorticity. Then, let's discuss the vorticity transport equation. By taking the curl of the Euler equation, it can be shown that the partial derivative of omega with respect to t plus u dot grad of omega is equal to omega dot grad of u. This is known as the vorticity transport equation. Now, let's move on to discuss circulation. Given us velocity field u and a closed curve c in space, the circulation of the flow around the curve c is defined to be gamma is equal to the integral over c of u dot ds, where ds is an element of arc length and is tangent to c. Note that ds is equal to t ds, where t is the unit tangent to the curve and ds is the increment of arc length. Now, let's discuss the relationship between vorticity and circulation. Consider a closed curve c in the xy plane with A the region enclosed by c. Using the definition of circulation and Stoke's theorem, the circulation is gamma, which is equal to the integral over c of u dot ds, which is equal to the double integral over A of the curl of u dot k dA, which is equal to the double integral over A of omega dot k dA. Then, let's discuss Kelvin's circulation theorem. Let an inviscid incompressible fluid of constant density be in motion in the presence of a conservative body force F, which is equal to minus grad chi. Let C of t denote a closed circuit that consists of the same fluid particle as time proceeds. Then, the circulation gamma is equal to the integral over c of u dot ds around c of t is independent of time. Now, let's discuss Lagrange's theorem. It is an important consequence of Kelvin's circulation theorem that for an inviscid flow which is irrotational at time t equals 0, it remains irrotational for all time greater than 0. Next, let's discuss free surface flows. A free surface is a boundary which is unknown in advance and must be found as part of a solution to a problem. An example of this is periodic gravity waves on a liquid surface. The free surface of the liquid is taken to be z is equal to eta of x and t. The undisturbed, i.e. wave-free, surface is taken to be z is equal to 0. We say there's a solid wall as z is equal to minus h. Note that periodic means that eta of x plus l with t is equal to eta of x with t for some l. So we assume that we can write eta is equal to a sine kx minus omega t, where the distance from crest to crest is called the wavelength lambda, the wave number k is defined to be k is equal to 2 pi over lambda, and the angular frequency is omega. We assume the flow of the liquid is irrotational and incompressible. Therefore, we can define a velocity potential such that u is equal to grad phi, and furthermore, the flow satisfies Laplace's equation. Note that there are 3 boundary conditions. First, we have that there is no normal flow at the bottom. The lower boundary is that z is equal to minus h. This has upward normal n is equal to k. So the boundary condition is u dot n, which is equal to u dot k, which is equal to grad phi dot k is equal to 0. Hence, the partial derivative of phi with respect to z is equal to 0, as z is equal to minus h. We also have the dynamic boundary condition at the free surface. We demand that the fluid pressure at the free surface is equal to the atmospheric pressure P naught. Thus, Bernoulli's equation for irrotational flow dictates that P plus rho of the partial derivative of theta with respect to t plus a half u squared plus gz is equal to f of t. So, applying Bernoulli's equation at the free surface, we have that the partial derivative of phi with respect to t plus a half u squared plus gz is equal to f of t minus p naught over rho, which is equal to g of t. We can set g of t to equal 0 without loss of generality. So, we are left with the dynamic condition on the free surface that the partial derivative of phi with respect to t plus a half the modulus of grad phi squared plus g eta equals 0 on z is equal to eta of x and t. Thirdly, we have the kinematic boundary condition. We have that a fluid particle on a free surface stays on the surface. This means that the flow moves with the fluid. If we describe the surface as f is equal to z minus eta of x and t equals 0, then f must retain its value of 0 as the flow evolves. That is, we must have that the material derivative of f is equal to 0. Hence, we must have that the material derivative of z minus eta is equal to 0, so the material derivative of z must equal the material derivative of eta. Thus, applying the definition of the convective derivative, we have that the partial derivative of eta with respect to t plus u times the partial derivative of eta with respect to x is equal to w. Hence, the partial derivative of eta with respect to t plus the partial derivative of phi with respect to x times the partial derivative of eta with respect to x is equal to the partial derivative of phi with respect to z on z is equal to eta of x and t. Now, let's state the water wave problem. First, the Laplacian of phi equals 0. Second, the partial derivative of phi with respect to t plus a half times the grad of phi squared plus g eta equals 0 on z is equal to eta of x and t. Third, the partial derivative of eta with respect to t plus the partial derivative of phi with respect to x times the partial derivative of eta with respect to x is equal to the partial derivative of phi with respect to z on z is equal to eta of x and t. And fourthly, the partial derivative of phi with respect to z is equal to 0 on z is equal to minus h. Then, let's consider the small amplitude wave simplification. The water wave problem is considerably simplified by assuming small amplitude waves, so that a is much less than h. The problem reduces to, first, the Laplacian of phi is equal to 0, second, partial derivative of phi with respect to t plus g eta is equal to 0 on z is equal to 0, third, the partial derivative of eta with respect to t is equal to the partial derivative of phi with respect to z on z is equal to 0. Fourthly, the partial derivative of phi with respect to z is equal to 0 on z is equal to minus h. We have already assumed that eta is equal to a sine kx minus omega t. Then our problem for phi is equal to phi sub xx plus phi sub zz is equal to 0 with minus h less than z less than 0. With the partial derivative of phi with respect to t equaling minus g eta, which equals minus ag sine kx minus omega t on z is equal to 0, and the partial derivative of phi with respect to z equaling partial derivative of eta with respect to t, which is equal to minus a omega cos kx minus omega t on z is equal to 0, and the partial derivative of phi with respect to z equaling 0 on z is equal to minus h. We seek a solution of the form phi is equal to f of z cos kx minus omega t with f dash of 0 equal to minus a omega and f dash of minus h equal to 0. Substituting into Laplace's equation, phi sub xx plus phi sub zz equals 0 implies that f double dash of k squared f times cos kx minus omega t is equal to 0, and so the second derivative of f minus k squared f is equal to 0. The general solution of this ordinary differential equation can be written in several equivalent ways. For example, f of z is equal to a e to the kx plus b e to the minus kz, or f of z is equal to c cosh kz plus d sine kz, or f of z is equal to e cosh kz plus alpha, where a, b, c, d, e, f, alpha are constants determined by the boundary condition. The form which is most convenient depends on the boundary conditions. Here, we choose f of z is equal to e cosh kz plus alpha. First, consider the no normal flow condition. This condition is that f dash of minus h equals 0, which gives that alpha is equal to kh. So f of z is equal to e cosh k times z plus h. Second, consider the kinematic boundary condition. This requires f dash of 0 is equal to minus a omega, and so ke sine kh is equal to minus omega. So we have that E is equal to minus a omega over k sine k. Next, consider the dynamic boundary condition. This requires phi sub t is equal to minus g eta on z is equal to 0. So minus a omega cosh kh over k sine kh times omega sine kx minus omega t is equal to minus ga sine kx minus omega t, which is true for all x and t, provided omega squared is equal to gk tanh kh. So we have obtained a travelling wave solution eta is equal to a sine kx minus omega t, provided omega depends on k, such that omega is equal to capital omega k, where capital omega k is equal to the square root of gk tanh kh. This is known as the dispersion relation for the problem. Note that the wave crests travel at speed c that depends on the wave number k. C is equal to omega over k, which is equal to the square root of g tanh kh over k. Waves whose velocity depends on the wave number are known as dispersive waves. Now, let's define phase velocity and group velocity. For a dispersive relation omega of k, the phase velocity is the speed of the wave crest c, also denoted Cp, where Cp is equal to omega over k, and the group velocity is Cg, where Cg is equal to the derivative of omega with respect to k. The group velocity describes the speed with which a wave packet containing several different waves of different wave numbers moves collectively, i.e. as a group. And, as ever, thank you for watching.